Our next step is to look at process planning, which includes all the engineering necessary to facilitate the processes necessary to produce our product. When we look at our process model, the question that we're asking at this stage is, what do you need to know about your process? Our model was quite simple in terms of producing scrap, producing waste, and producing acceptable product. But now we have to ask ourselves this question: what do we need to know about this process in order to make this something that can produce the characteristics that we're trying to achieve? If we look at our process, we have to think of it in terms of a number of engineering specifications that will help us describe what will happen during that process. And so it's going to include every element necessary for production at each individual process. The decisions that we make at this time are going to have a profound impact on our lead time to production. In other words, how long does it take on a time scale from the time that we get a stable design specification and until we have all the engineering specifications for our manufacturing system. That's what we're calling our lead time until we can actually produce our product. What's involved in process planning? Well, as you can see, there's quite an exhaustive list of items that we need. First of all, we need to have all our manufacturing processes specified, and associated with that, all the process parameters. So in IE 274 or 248, you learned about things like feed rate, spindle speed. So when you think about process parameters, you think about those settings that are going to achieve the characteristics based upon the design specification. It will also involve equipment, especially machinery, as well as other types of control equipment, tooling, which is a very broad category, jigs, which are a special type of tooling, which we'll mention, and then fixtures, which also is a special type of tooling. Machine instructions, we're talking about software here. Someone has to write code because a lot of our equipment that we're using in our manufacturing processes involve machine instructions of a variety of types, and you'll get a little experience with that using NC programming. Well, in your project, you've already seen the necessity to create operator instructions for training purposes and to ensure that all operators are following the same process. The operations process chart shows us what processes are adding value to the product. And then we'll look at the material flow process chart, which incorporates other support systems necessary to produce the product. Well, when you look at the manufacturing processes, you have to narrow it down fairly quickly to those processes that are feasible. So just by the geometry and the material that's being used in the design specification, it automatically eliminates a number of processes. Here you want to think about the notion of near net shape, which essentially says we create the final geometry in one step. Now that is the ideal, to only perform one process and create all the characteristics of your geometry and material properties necessary to satisfy your design specifications. If that's not possible, then you have to think about how many processes are absolutely necessary. Don't forget, as you increase the number of processes, looking at your process model, then you're going to compound the effect of the scrap rate S. And of course, that, as we've already seen, adds to the total cost of your product. So it is advantageous to only have one process if at all possible. If not, then you have to think about the sequencing. So what are the individual steps that have to be performed? Of course, this is very important when it comes to assembly and other joining processes such as welding. The other attribute that you're going to have to consider is the cost effectiveness, and by this we mean minimize the overall cost of the product, of producing that product. We understand, hopefully at this point, that cost pressure is relentless. And therefore, we need to keep that in mind when we select processes. If you're choosing a process that is very costly because of either equipment or the direct labor content or indirect costs, then that's probably not a good choice. Of course, scrap rate is always a factor, and how much waste we're producing as well. So it's something that you have to consider in selecting the processes. We also worry about the cycle time, and there, of course, we're concerned about how responsive our system is, because this will affect our manufacturing lead time, the time to get it into the hands of the customer. So if we have a process that has a very long cycle time, and we have an alternative with a much shorter cycle time, then that may be preferable, again, considering cost factors and scrap and other types of contributions. Well, we already understand the effect of scrap rate, hopefully. So 1 minus S, the good parts that are going on to the next process, that will be a large impact on the system. Therefore, you'd like to have the highest yield possible, which means the smallest value for S. For any process, it's good to find the optimal process parameters, and of course this depends upon the nature of the process. So in 248, you learned about feed rate and spindle speed. So what are those parameters that will give you the optimal outcome? Now when we use the term optimal, we have to be careful because it may not be exactly optimal, but we're looking for what we think is the best solution, because some of the parameters may be in conflict with each other. When we consider tooling, it can be a major cost, again, depending upon the nature of the product that we're producing. What we include in tooling is anything you need to perform work. In other words, we're adding value. So if it's involved in the adding of value during the process, then we're going to categorize it as tooling. Well, we have standard tools, which are important because going back to Design for X, you already understand the principle that it would be nice to use always standard tools. But that is not always possible, and so in some cases we'll have to come up with special tools. Case in point, if you're using dies and molds and those kinds of tools, those will be developed custom to the product. So typically you're going to have to go outside to a vendor and purchase a custom tool, which requires some degree of fabrication, and that usually costs a significant amount of money. Especially for large dies, it would not be unusual to pay $500,000, and so you can see the tooling costs increase significantly because of the process that you have selected. Now, does that mean that that's a bad process? Well, it may turn out that based upon that die and the ability to reduce scrap and also decrease cycle time, that may be a less costly process than the alternatives such as machining or some other forming process. When you look at the process at that particular step in your production, you're thinking about what tools are absolutely necessary. Because what you'd like to do is minimize the number of tools, because that will minimize the potential errors as well as the cost per part, as you've seen already. And then when you look at the individual tools, make sure that they're cost effective so that you're not buying complex, difficult to use tools or very expensive tools that are unnecessary. Jigs are a special type of tool, and the primary purpose of a jig is to guide tools. And here you see a very famous national product made here in Iowa, the Craig jig, that allows you to create holes for a joint at a very specific angle. And you can see here, hopefully, there are bushings in this jig that guide the drill bit. And so the operator is pushing the drill bit through the bushing, and because it's clamping the product against that surface, therefore establishing an orientation for a datum, we get a very precise orientation and location of these holes. And so that's the goal of the jig, to guide some type of manual tool path. At the same time, we're also presenting the workpiece in the right orientation and location, and of course preventing motion of the workpiece, which would defeat the purpose of creating that orientation and location and create a lot of deviations in the final outcome. A fixture is also a special type of tool that we're going to use for holding a workpiece. And by holding a workpiece, what we're saying here is that we will maintain an orientation and location, and hopefully at this point, what you're thinking of is datums and a datum reference frame. So we want to establish features and surfaces such that we maintain the proper orientation location of the feature we're trying to create, and of course at the same time prevent workpiece motion. So it sounds like a fixture is a jig, except there is no tool consideration in terms of guiding the tool path. I mentioned machine instructions because a lot of equipment that we're purchasing today has some type of program that is necessary to control a process. When you look at these types of programs, and there are many different types, typically you're going to have some geometry involved in terms of your program. Also parameter settings for the process itself in terms of dials and adjustments on the equipment. And if you're dealing with geometry, usually there's motion involved in terms of moving a tool. And then finally, error conditions. When something goes wrong, we need to alert operators with alarms, whether it's a visual alarm or something they can hear, or we could send them an email, send them a text message to different people to make people aware that there is an error condition on that piece of equipment. Operator instructions, we need to have material describing what the operator has to do during this process. So all the steps required for a given operation. Now, of course, the level of detail, you have to be cognizant of the fact that the operator typically is a skilled operator and therefore doesn't have to be told every step in minutia, but what are the major or significant steps in performing the operation. Of course, associated with that is the sequence in which it needs to be performed, especially if there's precedent requirement, and any tooling that's required to complete the operation, as well as settings on equipment used in that process. Well, where do we start? The easiest place to start is with an operation process chart. Here we're going to specify all the manufacturing operations necessary to produce a part. And by that, we are referring to those operations that produce value. When you look at the operations process chart, what you're really talking about is a routing sheet. The routing sheet is what's used in the actual operation when you're producing product, and so the product is tracked with that routing sheet, and we know exactly where that product is at each stage in our operations. Every process where we're adding value and inspection needs to be defined. When we define that, we're going to show where direct material, and only direct material, enters the operation. Well, how do we begin this process? What we do is we start with the exploded bill of materials, and that will provide us with some structure, and then we define those operations that will create the parts associated with that bill of materials. An operation is specified by giving it a unique identifier, in this case O-1, and then a description of what is occurring in that operation. If we're doing an inspection, then it's going to be a square with a unique identifier I-1, and that will define all inspections that are performed as we go through our system. When you think about operations, you should think about those processes that add value. So you can see some very simple processes here. We're driving a nail into a piece of wood and joining that with another piece. So we are transforming this material by adding direct material, and that would be indicated by a line. And coming out of that, we're going to have another line indicating that the material has changed. So during an operation, the key differentiation here is there has to be a change in value. If there's no change in value, then it should not be an operation. So I'm drilling a hole here where we are removing material, and therefore we see a change in value. Or you're typing a letter, you're creating content, you're producing something, so there's a change in value. That would be considered an operation. For inspection, we have a non-value adding operation, essentially, where we are looking at this product and we're doing some type of assessment to determine the quality or quantity that was produced. Or we might be reading a gauge, inspecting that gauge and seeing what the current value is, or perhaps assessing a form to make sure it has the right information on it. Again, it deals with quality and ensuring that what happened in an operation was what we expected to happen, and therefore the outcome would result in moving that product on to the next stage in the process. When you look at an operation, the lines here will indicate unique direct materials. So every line you see entering an operation or exiting an operation represents different direct material. This material represents material coming from somewhere, and that could be inventory, that could be from some type of storage system. And this line here would indicate material coming from perhaps a previous operation. And then something happens in our operation to change the material, and now what is exiting is not the same because we've had this delta in value. At the same time, we see that time is changing based upon the cycle time of the operation. And therefore, the operations process chart shows you how time is incrementing, and that will affect, of course, the manufacturing lead time. Note, again, the state of the material changes during the operation, and therefore either geometry or material properties are changing. For inspection, we are assessing different attributes of the part depending upon what we are examining after that operation. And we are comparing our results with the design specification. The primary question here, did you achieve what you were trying to achieve in that operation? Note, no material is being added. There's no change in the state of this material. So the material entering this inspection is exactly the same as the material exiting. And therefore, it is a non-value adding operation. We have time incrementing, so it does add to our manufacturing lead time, and it can be significant depending on how difficult it is to perform the inspection. So we end up getting something that might look like this, where we start off with two parallel, and note that this structure here should be consistent with your exploded bill of materials. And here we see a parallel system to this. They're feeding together and aggregating during this operation, and then we have a final inspection. Our lines, again, indicate direct material that's entering the operation, and then we're changing the state of the material, inspecting, and final aggregation, and then inspection. Of course, the complexity of the product will affect how complex this structure is. So I could have many branches on this tree structure, but it always tends to be hierarchical in nature. So key concepts here are process planning is a critical phase of developing a new product. To start off, we'll use an operations process chart to give us a structure on which to base our manufacturing system. Contained in that operations process chart, we'll have all value-adding processes and inspection to ensure that that process was successful. So in summary, you need to engineer every single element that is necessary to support your process. And that goes back to our original process model, including rework. Our operations process chart will show the flow of direct material, and only those operations that add value will be included. Inspection does not add value, but we will specify it to indicate those stages in which we'll perform inspection.